Okay, we've been talking about electron configuration, I think. So, in addition, we also talked about waves in this chapter as well. And we had a few equations. C is equal to the wavelength times the frequency. And again, ultimately, what we were talking about in this chapter is electrons sort of transitioning from lower states of energy to higher states of energy. And as they kind of relax back down, they will give off that energy in the form of a photon of light, which will correspond to a specific wavelength. And here we have our speed of light, which 2.9979, I think, times 10 to the 8 meters per second. The wavelength here is in meters, and the frequency here is in reciprocal seconds. And this allows you, if you know the wavelength, to figure out the frequency, if you know the frequency, to figure out the wavelength. We also talked about the energy associated with it, which is E is equal to h times the frequency. H is a constant as well. That is Planck's constant, 6.63 times 10 to the minus 34 joules times seconds. And this also allows you, if you know the frequency, to figure out the energy associated with that wave. You can use both of these equations together, and E equals hc divided by the wavelength. And since both of these are constants, if you know the wavelength in this case, you can also figure out the energy. Wavelength here does still need to be in meters for everything to properly cancel out. So you can figure out the energy associated with that. You can figure out the frequency, the wavelength, and so forth. What we talked about is this idea of quantized energy, which means electrons will gain and lose enough energy to completely transfer from one energy level to the next. They will never find themselves sort of between energy levels or anything like that. They will fully make that transition, either upwards or downwards. It could go obviously both ways, but they will lose or gain enough energy to fully make that transition as described by this equation here. Where it comes off in terms of the wavelength as it is transitioning could be part of the electromagnetic spectrum that we talked about. And remember, electromagnetic spectrum, we have things like radio waves, we have things like microwaves, we have things like IR, the visible part of the spectrum, the UV, the X-rays, and the gamma. And remember, the visible part of the spectrum is sort of where we see colors like Roy G. Biv, right? And the relationship we talked about with waves is the longer the wavelength, which actually would be on this side, longer the wavelength, the lower the frequency, and the lower the energy. And on this side over here, where we have gamma rays, this would be short wavelength. It'll be a high frequency, and it'll also be a high energy. So that is the relationship between those things, the wavelength, the frequency, and the energy. And that even goes with colors. As we talked about, red actually is lower in energy than, say, violet. But if that wavelength coming off does fall in this visible part of the spectrum, again, we will see some type of color associated with it. So we talked about a couple of things, and we moved away from sort of Bohr's model of the atom to this more quantum mechanical model of the atom, where electrons are basically found in what are referred to as orbitals. And we find electrons in what are known as orbitals or atomic orbitals. And there's a few different types of orbitals. There are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. And any individual orbital could hold basically only 2 electrons. And remember that the s orbitals start on the n equals 1, or the first energy level. The p orbitals start on the second energy level, the d orbitals start on the third energy level, and the f orbitals start on the fourth energy level. There's only one type of s orbital on any energy level, there's actually three types of p orbitals: px, py, and pz orbitals. There are 5 different types of d orbitals, and there are 7 different types of f orbitals. Now, when you have orbitals where there are multiples, individual orbitals on the same energy level, those are what are referred to a lot of times as subshells or sublevels, like again the 2p subshell. That would be all 3 of those electrons together, orbitals together. That means we can max out our electrons since there's only one type of s orbital, 2. There are 3 different p orbitals, so we can max out with 6. There are 5 different d orbitals that we can max out at 10. As we also talked about, electrons go in opposite directions. And lastly, there are 7 f orbitals that we can max out with 14 electrons. Again, you don't have to max out your orbitals or subshells, but these would be the maximum you could put into those subshells: 2, 6, 10, and 14. So as we talked about, if you know basically the different orbitals, you know how many electrons you can put in there, you pretty much can write any type of electron configuration you want. There is a distinct order at which the electrons go into the atom. And if you remember basically this right here, this will allow you to create that order for you. So as I mentioned before, all you have to do is go, okay, 1s, go down a little bit, 2p, down a little bit, 3d, down a little bit to the right, 4f. And then basically all you have to do underneath each of those is just fill in the numbers to like 7 is good. And this will give you the order at which electrons go into the atom. And the major place where people screw up is right here. Once again, the 4s is actually lower in energy than the d, and that pattern follows. Again, the s lower in energy than the d. So the s's will get the electrons first, and then they'll go back to the d. Now, we finished up last time kind of talking about electron configuration and what's referred to as orbital diagram. And I think we got to carbon, which is 6. And a reminder that if we're going to do it, we always start here and then we just continue to zigzag until we fill everything. So 1s2, 2s2, 2p4 in this case. And that will give us our, that's too much, 1s2, 2s2, 2p2 would be a much better math there. 2p2, there you go. And that will get us our 6 electrons up on top. And we could draw our orbital diagram by drawing boxes or lines. Again, to truthfully do it correctly, should kind of go up with energy, but I'm just going to go sideways here to save space. Remember, first one goes up, second one goes down, first one goes up, second one goes down. And remember, when we do have a subshell where there are multiple orbitals that make it up, Hund's rule tells us that we go up first, which gives us parallel spin, and then they come back and pair off. Any questions on that one there? All right, then let's continue through. So we'll continue down the first 10 here. So nitrogen, which is 7. So once again, we're going to start with our electron configuration here. So that is 2, 4, and obviously we could fill the rest into there. So that is going to give us 1s2, 2s2, 2p3 at this point. And again, this tells you how many electrons there are in the subshell or orbital. That tells you the orbital or subshell. And that tells you the principal quantum number, which is the energy level. With nitrogen, we have 2 electrons on the first energy level, and we have 5 electrons here on the second energy level, which are its valence electrons. And if we were to do our orbital diagram here, we're going to go up, down, up, down. At this point, up, up, and again, we will continue in the upwards pattern here. At this point, we have no option. We're going to have to start pairing up at this point. But again, we do want to fill the subshells one at a time in the upwards direction. Any questions on that one there? Yeah. So let's take a look then at the next one, which is oxygen. So oxygen has 8, so that would be 1s2, 2s2, 2p4. At this point, oxygen has 6 electrons in its highest energy level, which is its valence electrons, and has 2 in the lowest. And if we were going to do our electron configuration here, again, up, down, up, down, up, 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 and now we come back to the first one on the left here, and that is where we place our next electron. We, as you can see, have basically room for 2 more electrons in that subshell before it is full. So let's finish it out there for the first 10 here. Fluorine, which is 9, would then be 1s2, 2s2, 2p5. Again, if you count up the top numbers, 5, 2, 7, and 2 is 9. Here again, if we put in our orbital diagram, up, down, up, down, up, 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 down, and down. As you can see, we got pretty much one more spot for an electron to kind of fill that subshell before it is obviously filled, and we would have to go to the next one, which would be 3s at that point. So let's take a look at that, which is number 10 here on neon. And if we get to neon, we got 1s2, 2s2, 2p6. Again, neon has 8 electrons, which is valence electrons, and 2 core electrons, which are the lower energy electrons. And if we were to draw our orbital diagram here, we're going to go up, down, up, down, up, 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 and down, down, and down. Okay, let's take a look. So we're going 18 on this one. So we can go 1s2, 2s2, 2p6. That's what we did previously. That got us to 10. So we want 2, 4, and 10. We obviously need to go to 3s next and zigzag there, the 3p, I think. So we'll go 3s2, which is 12, and then the 3p6, which is 18. In this case, argon has 8 valence electrons there in the third energy level, and these would be as core electrons on the bottom. We're going to do our orbital diagram. Obviously, we need some boxes for everybody here. And again, we would go up, down, up, down, up, 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 down, 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 up, down, up, and then down here. Any questions on that one there? Yeah. All right, so if we look at something like this, one of the ways that electrons are added to the atom is much like how protons are, one at a time. As we've been talking about, sort of this build-up idea of electrons are added lowest energy orbitals first, and they continue to the higher ones afterwards. Now, if we look at something like potassium, which is 19, we would have 1s2, 2s2, 2p6, 3s2, 3p6, and at this point we would then need to zigzag back to 4s1. So a reminder that 4 comes before the 3d. So that is what comes next. By the way, that would mean here potassium has one valence electron, which is in the highest energy level. Now, if we look at the electron configuration as we just saw on the previous slide, up until this point here, that is 18 electrons. And as we saw before, that 18 electrons was argon's configuration. So there is a shorthand that you can do when you write electron configuration. And you could take the noble gas that comes right before it, which in this case would be argon, and you would continue with the electron configuration after it. So the argon in the brackets represents the electron configuration for argon, and then you continue on with it. So that is a shorthand or shortcut way of writing electron configuration, sometimes referred to as noble gas sort of configuration. The reason for that is it has to be a noble gas that's in the bracket. So it has to be the noble gas that comes right before the element you're trying to write. So for example, if we were doing magnesium, which is 12, 1s2, 2s2, 2p6, 3s2, this part of the configuration is 10 electrons. We just count up the top. And 10 electrons is neon. So we could shortcut this as neon 3s2. So it always has to be the noble gas that comes right before whatever element you're going to write the electron configuration for. If you were doing something like phosphorus, which is number there 16, right? Phosphorus 15. 1s2, 2s2, 2p6, 3s2, 3p3. Once again, this would be where you would have to do your noble gas configuration, which is still neon, and just continue on 3s2, 3p3, and so forth. So you can do sort of a shorthand of electron configuration. And again, it does has to be a noble gas that goes in the brackets. And it can't be the one after it. It has to be the one before it. Any questions on that there? Yeah. Now, when we talk about transition metals have incompletely filled d orbitals or completely filled d orbitals. And there are a few exceptions to electron configuration that we come across with transition metals. And the two most common ones that you need to know is chromium and copper. And if you did chromium, which is 24, and you just wrote the electron configuration for chromium following our chart, you would get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. And if you wrote the electron configuration for copper, just following our little chart, you would get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. By the way, you could shorthand these like we sort of have on the bottom. Up to here again is 18, and that would be argon 4s2, 3d4, or argon 4s2, 3d9. Now, where is the exception? The exception actually has been found experimentally that it actually will have one less electron in the s orbital and one more electron in the d orbital. And what that ends up doing is giving us our configuration as we see on the bottom there, argon 4s1, 3d5, that essentially fills up all the d orbitals with individual electrons for chromium. And for copper, 4s1, 3d10, is the exception there. So this has experimentally been found to be more stable in that way. Maybe wondering how can that sort of be? It can be because of this. When you have the electrons coming into the atom, the 4s and the 3d orbitals, they're like really close in energy, and the 4s orbitals are lower in energy, so they will actually get the electrons first. And then it's not very hard for one of those electrons to kind of go upwards because they're really, really close in energy. What actually happens, as we'll talk about in a second, is actually when you start to fill the d orbitals with electrons, the energy of these orbitals actually switch. And the 4s ends up being higher in energy than the 3d. And it actually does switch energy when that happens. But they're very, very close in energy to begin with. And that is why sometimes you'll see electron configuration written based on energy, because there is that switch that occurs. And as we talked about, you should always write it based on filling order, which is what we're talking about here. So for us, chromium and copper will be the two that you need to know, which again are these. To be truthfully honest with you, if you look at where chromium is on the periodic table and you look at where copper is on the periodic table and you go down and in, there's a ton of exceptions for electron configuration. Silver's an exception. PD actually has no electrons in the S. They've all been promoted up to the D. So there's a lot of exceptions to the electron configuration below chromium and copper on the periodic table. But for us, in most chemistry classes you take, people are just kind of concerned with chromium and copper. So for us, we'll be concerned with that. For everything else, even though silver and some of those other ones are exceptions, you don't have to remember them for us. I won't say maybe online if they might want you to write the exception, but there are a lot of exceptions underneath there. Yeah. Yeah. Exactly. So what I underlined there is 2, 4, 10, 12, and 18 electrons. And 18 on the periodic table is argon, right? And that's the noble gas that comes right before chromium or copper. And that's basically what the bracket with argon in it means. It means that's the electron configuration for argon. And then you just continue on with the electron configuration for whatever you're writing it for. We're doing it for chromium, which is 24. So this right here represents 18. Actually, I'll do it here. This represents 18, and then this would be 19, and then this would be our uh, 24 electrons total, which is what we're doing for chromium. This would represent 18, and then 19, and then obviously 29 there for copper. Yeah. So typically, if you're going to kind of use the shorthand, you use the noble gas that comes before what you're writing it for, and then you just kind of continue on with the configuration after that. Other questions? Okay. So here you can see those exceptions we talked about in terms of the ending part of it. As I mentioned a second ago, there are a number of other exceptions that have been found experimentally. Again, for us, chromium and copper are the ones you do have to worry about. As you can see here, as I mentioned before, PD actually has no electrons there in the S. They've all been promoted up. This guy's got 1 and 1 as well. So again, kind of below chromium copper, in and down and into the left and right, a lot of similar exceptions. Now the lanthanide series on the periodic table is down on the bottom there, and that is where we get to our F subshell, and they have incompletely filled 4F subshells. And remember that these guys technically go, the guys on the bottom go right there in terms of where they should be in terms of it. And when we look at our periodic table, there are basically sections on it that you can read off the electron configuration if you know what you're doing. So, for example, group 1 and 2 on the periodic table is what is referred to as the S block, and S's have 2 electrons, right? So that is 1 and 2. Groups 3 through 8 is the P block, and P subshell, you can put 6 electrons. 1, 2, 3, 4, 5, and 6. The transition metals are the D subshell, and that's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And down here, our lanthanides and actinides are our F subshell. That's 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So the period numbers on the periodic table represents the energy levels. Yeah, they represent the N number, are the energy levels. So how you could do this, for example, is if you did magnesium, which is right here, and you wanted to do the electron configuration by just simply reading it off the periodic table, you would start up here and go 1s2 to the end. This would be 2s2. This would be 2p6 to the end, 3s1 and 3s2. And you could actually just read it off that way. 1s2, 2s2, 2p6, 3s2. If you wanted to do, say, sulfur, which is like right here, you would start at the top here and go 1s2, 2s2, 2p6 to the end there, 3s2, and this is 3p1, 2, 3, and 4. And you could just read off the electron configuration like so. Now, the problem with this is you do have to be careful because there are some issues that can happen. So let's say we wanted to do iron, which is like right here, I think. So if we were going to do iron here, we again would start up here, 1s2 to the end, 2s2, 2p6, 3s2, 3p6 to the end, 4s2. Let's go underneath. Now, when we get here, this is our D's, right? And D's start at what energy level? They actually start at the third energy level. So this is actually here 3D, not 4D. It's one behind the period number. That would be 3D. This would be 4D, 5D, 6D as you go that way. So that would be 3D, 1, 2, 3, 4, 5, and 6. So that's really important to remember. If you find yourself over here in the F's, that is 4F, which is 2 behind the period number where it technically goes. Since these guys technically go up into here, that would actually be 2 behind the period number. So you can count off on the periodic table if you kind of know what you're doing. You just got to be careful, when you get into the D's because they are 1 behind. And if you were to get into the F's as well, they're 2 behind as well. But other than that, you could just count off on the periodic table. Any questions on how to do that there? Yeah. So then let's talk about electron configuration for ions. So what happens when something does gain a charge? So let's take oxygen here. And again, if we had neutral oxygen, it is 8. So that is 1s2, 2s2, 2p4. Oxygen, as we know, is a -2 charge, which means it does have 10 electrons. which means its configuration 1s2, 2s2, 2p6 are that is neon's configuration. And if you look at something like magnesium, which we also looked at, which is 12, again, 1s2, 2s2, 2p6, 3s2. Magnesium, which is group 2, has a +2 charge. It has 10 electrons, which means it should have 1s2, 2s2, 2p6 are neon's configuration. That is, as we talked about with bonding, the purpose of it is for them to reach noble gas configuration. And you can see here our metal lost some electrons to do so, and our nonmetal gained some electrons to do so. They actually ended up with the same electron configuration. So oxygen with a -2 charge, magnesium with a +2 charge, and neon are all what are known as being isoelectronic with each other. They have the same electron configuration. Yeah. So if something has a charge, you need to adjust its electron count. If it is a representative element, like not a transition metal, it will end up at a noble gas, as we talked about. So it will actually end up at a noble gas. So if we had something like phosphorus with a -3 charge, the electron, why don't you write the electron configuration for that, and why don't you do it for, let's do lithium. So take a moment and write the electron configuration for both of those. Okay, let's take a look. So we look at phosphorus, which neutral phosphorus is 15. And again, with a -3 charge means it actually has 18 electrons. So that would be 1s2, 2s2, 2p6, 3s2, 3p6, or as we know, that is argon's configuration. And lithium here has 3 with a +1 charge. That's down to 2, which means it would be 1s2, or that would actually be helium's configuration. Any questions on that there? So what happens with the transition metals? It is a little bit different what happens with transition metals when they lose electrons. And let's talk a little bit about sort of what happens in the case of transition metals. And some of what happens has to do with what we talked about a second ago, which is there is sort of that energy switch that occurs once we start putting d electrons into those orbitals in terms of the energy. So when we have transition metals, when those electrons go in, as I mentioned earlier, they definitely go into the 4s as it's lower in energy, and then they start populating our d. When that happens, there is a switch in energy that occurs, and the 4s actually ends up being higher in energy than those 3d. And that's really important for how transition metals lose electrons. So, for example, if we looked at iron, again with no charge is 25, 26 there. Again, 1s2, 2s2, 2p6, 3s2, 3p6, again 4s2, 3d6. Now, what happens in this case, again, we could shorthand it if you like, argon 4s2, 3d6. When iron makes a +2 charge, for example, that means it has lost 2 electrons. And that means it will have 24 electrons. So if I just kind of put in our electrons over here in the picture, so say these are obviously iron's electrons. When it loses the electrons to make that +2 charge, it will always lose the s electrons first because they end up being higher in energy. And that means that we will end up with 1s2, 2s2, 2p6, 3s2, 3p6. Once again, we're going to lose these first, and we'll end up with 3d6 in this case. Argon 3d6. Now, one of the interesting things about transition metals are they have extra electrons, if you will, which means if they need to go further than 2 electrons, they can. So if I had iron with a +3 charge, that would mean it has 23 electrons. And what happens in this case is it will lose these 2 electrons. Now the next sort of highest in energy is actually the D's, and it will come in and take out a D electron at that point, and you will end up with argon 3d5. So what happens with transition metals is they will always lose the s electrons first, and then if necessary to lose more electrons, they will then go into the d orbitals and they will lose electrons from them at that point. Question on that there. So why don't you write the electron configuration for nickel with a +4 charge? 8. And I'll just do a shorthand. So argon, which gets me to 18. 4s2, which gets me to 20. Then 3d8, which gets me to 28 there for nickel with no charge. Now, nickel with a +4 charge means that it has 24 electrons. So once again, because it's a transition metal, we will lose the 2 electrons here first. And then we're going to take the other electrons out of the D, and that will leave us with argon 3d6 for our nickel with a +4 charge. Any questions for that there? All right, same idea here with Mn. Mn with no charge is 25. So that's going to be argon 4s2 3d5. Mn with a +2 charge is going to have 23 electrons. So once again here, we're going to get rid of the 2 electrons there. And that will then give us argon 3d5 in this case. Or obviously you could write the entire configuration out without this shorthand. Any questions on transition metals? So again, as we talked about, I think previously as well, transition metals do not get back to noble gas configuration because they have a lot of valence electrons. Representative elements will get to a noble gas configuration if they do make charges, but not transition metals. Any questions on that? And that pattern follows all the way through here. If you're going through any of these guys will always be lost first, and then you'll dip into kind of over here if necessary. Any questions on electron configuration for ions? Okay. All right, the next thing we're going to do is talk about some periodic trends. And one thing we're going to talk about is valence electrons. Valence electrons is the highest energy level electron, is the outermost electrons found in an atom. And you could get them one of 2 ways. You could write the electron configuration as we see here for nitrogen, 1s2, 2s2, 2p3. Remember, the first numbers are the energy levels. So here we have the second energy level, and there are 5 electrons there. So that would be the 5 valence electrons in nitrogen. These would be the core electrons in this case. The core electrons are closer to the nucleus. They're held tighter. They are not involved in bonding. Valence electrons, as we know from the bonding chapter, are the ones that are involved in ionic bonding and covalent bonding as well. Any questions on that there? Now, you could write the electron configuration for everybody to figure out the valence electrons. So if you did that, you can figure it out. But a much easier way is the valence electrons does equal the group number. So the group number on the periodic table equals the valence electrons. So fluorine is group 7. It has 7 valence electrons. Chlorine is group 7, has 7. Carbon is group 4. It has 4 valence electrons. By the way, that also goes for transition metals. I think maybe I have a periodic table there that might work. Right here. We'll go here. And if you're doing sort of the transition metals, we actually do like the 1 through 18 numbering, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then you go 13 and whatever. But for transition metals, we use this numbering here. So if you think about iron that we just sort of wrote its electron configuration for, iron, which is 26, argon 4s2, 3d6. That is the 8 valence electrons that iron has. If you did Mn, which we did, I think, a second ago, Mn again is argon 4s2, 3d5, and that is its 7 valence electrons as well. So when you're doing transition metals, the number of valence electrons equals kind of the 1 through 18 numbering, or 3 through 12 if you want to think about it for transition metals. That is how you could quickly get those. The good thing is, as you might know from the bonding chapter, we really don't deal too much with transition metals when we're doing like bonding and stuff like that. So you don't have to worry too much about it. But if you needed to figure out the number of valence electrons there for guys here in the transition metal, that's how you do it. It even works for the exception like chromium, which is argon 4s1, 3d5, 5 and 1 is 6. And that is, again, what we see here for chromium in terms of its valence electrons. Any questions on that there? So as we talk about the periodic table, metals and nonmetals, as we go down a group, especially with the metals, they do tend to give away their electrons a lot easier. So cesium will lose its electrons easier than, say, lithium. And this is because the outer electrons are further away from the nucleus and they're not held as tightly and they can be removed pretty easily. When we talk about nonmetals and sort of activity and reactivity, upper right of the periodic table is where we find our most reactive nonmetal, which is our friend fluorine, is really our most reactive nonmetal. So we're going to talk about some periodic trends and why these things explain what we see happen with metals and nonmetals. So the first thing we're going to talk about is what's known as effective nuclear charge. Effective nuclear charge is the positive charge that outer electrons feel as a result of what's known as shielding. So if we take a really easy example like lithium, which has 3 electrons, it has a 1s2, 2s1 configuration. It has 1 valence electron, and it has 2 core electrons. And if we take our nucleus for lithium, which is +3 because it has 3 protons, I'll just draw these. It's not exactly obviously how they look, but we'll just kind of draw it like this for the sake of this drawing here. On the first energy level, I have my 2 core electrons. Second energy level, I have my valence electrons. So what happens in this situation is my core electrons pretty much are right up front and center, and they're going to feel the full brunt of that positive 3 charge. And the strength of positive and negative attractions increases with size. So the larger the positive charge, our negative charge, the stronger the attraction is. So those two core electrons are definitely going to be held really tightly because they are feeling that full brunt of the positive 3 charge. Now, when we get to our valence electron, he experiences what is known as shielding. And he is shielded from the full positive charge of the nucleus by these lower energy electrons. So these lower energy electrons kind of get in the way. And because they're in the way, that outer electron doesn't actually feel the full positive charge. So you can actually calculate the Z effective by taking the positive charge of the nucleus and then subtracting the negative charge of the electrons. And there are 2 electrons that are shielding here. And that gives us a +1 charge. So what that means is instead of this outer electron feeling a positive 3 attraction to the nucleus, it is actually only feeling like a +1 attraction to the nucleus. And what that means is it's going to be held not as tight as those core electrons. And that's why valence electrons, for example, are the ones that can be used in bonding because they're not held as tightly because of that. On the periodic table, in general, Z effective increases as you go up and to the right and decreases as you go down and to the left. So the effective nuclear charge increases to the right and decreases to the left. And that also has a lot to do with size. The greater the positive charge to the right, because they have more protons, is going to bring in even the outermost electrons closer to the nucleus and give it an overall smaller size. Another important periodic trend is what's known as ionization energy. Ionization energy is the energy required to remove an electron from the gas phase. And that's what's happening here. We have a metal, for example, loses an electron, becomes positively charged. Metals have really low ionization energy. Nonmetals have really high ionization energy. The general trend on the periodic table is as you go up and to the right, it increases. As you go down and to the left, it decreases. Now, when we talk about electrons being lost, they actually are lost one at a time. They don't all fall off at once or get lost at once. So, for example, if we took magnesium, the first thing that would happen is magnesium would lose 1 electron. Then that magnesium that has lost 1 electron would then lose a second electron. And when it loses the first electron, that is what is known as the first ionization energy. That's the energy to remove the first electron. To remove the second electron, that's known as the second ionization energy. And then what would happen is this guy would then lose another electron, and that would be the third ionization energy. So electrons come off one at a time. Is it easier to remove the first electron or the last electron? Which one's easier? It is easier to remove the first electron, right? Because when you lose an electron, what happens to the overall size of the ion? It gets smaller, right? Because the electron cloud decreases. So it gets smaller, everybody gets moved in. Now those outer electrons are closer to the nucleus and it's going to be held tighter and harder to remove. When you lose the second electron, it moves in even closer. And then it gets harder and harder. So it gets harder and harder every time you remove an electron. And the trend that we see is the first ionization energy is smaller than the second, and the second is smaller than the third, and so forth. So the ionization energy increases as you keep removing electrons. So for example, if we look at our magnesium, we could see that the first ionization energy is 735, and that's the energy required to remove the first electron. Then once you get the first electron off, you're now at about 1400 kilojoules of energy to remove the second. It almost doubled in energy to try to take off the second one. Now look what happens when you try to jump to the third electron. You go from like 1000 or so to about 6 or 7 times the amount of energy required to do so. And by the way, that doesn't happen, and that is why magnesium, for example, forms a +2 charge only, because once you get there and you get rid of its 2 valence electrons, you're now into the core electrons at this point. And it's good luck trying to remove those. It's just not going to happen. So that's why, for example, something like magnesium will only lose 1 electron or 2 electrons. Something like sodium will only lose 1 electron, because as you can see here, as you go from the first electron in sodium, it is now like a tenfold jump in energy to try to remove that core electron. It's just not going to happen. So that's why certain things have fixed charges that we think about, and it has to do a lot with the ionization energy, because once you get to those core electrons, it's just not energy efficient for them to lose them because they're held so tightly, and they typically don't do that. That's also why, for example, aluminum makes a +3 charge, because you can see after the third electron, you go from 2700 to about 11,000 in terms of the energy required to do so, and that's not going to normally happen. So that again is why certain things have fixed sort of positive charges, because of the ionization energy. You could also see very high ionization energy for our nonmetals, and that's because our nonmetals don't typically lose electrons, right? They typically gain electrons. Any questions on that there? Now, electron affinity is the actual energy change that occurs when somebody gains an electron. So ionization energy we think of as being involving with cations. Electron affinity is what we think of as being involved with anions, when things actually gain electrons. And if you have a high electron affinity, that means you like to gain electrons. And when we look at the periodic table, the general trend for electron affinity is it increases as you go up and to the right, and it decreases as you go down to the left. And in general, things up to the right will have a high electron affinity, which means they like to gain electrons. It is not a perfect trend. For example, if you looked at group 7, electron affinity increases as you go towards fluorine, but then it kind of decreases a little bit and then increases. But it's the general trend that occurs. Now, electron affinity should not be confused with electronegativity, like we talked about in bonding. Electronegativity is the ability of an atom to bring electrons towards itself. And as you know, on the periodic table, it increases as you go up and to the right, with fluorine being our most electronegative, and decreases as you go down. So these two things are similar to each other, but they are different things. One is the ability of an atom to bring electrons towards itself. The other one deals with the atom actually gaining electrons, which is the electron affinity energy change that occurs. One last trend that sort of helps us understand what's going on is atomic size. By the way, when we make an anion, the size of the anion is larger because it gained electrons, right? As opposed to when we make a cation, it is smaller because they lost electrons, compared to the neutral atom. Now, atomic radius increases as you go down, and decreases as you go to the right. So it decreases as you go up and to the right, and increases as you go down and to the left. And again here, that is because of, for example, effective nuclear charge. As you go up and to the right, the effective nuclear charge increases, which means even those outer electrons are still going to feel a stronger pull towards the nucleus than those guys to the left on the periodic table. And that's going to bring everybody in tighter to each other. So even those outer electrons are going to be closer to the nucleus, and the overall size is not going to be larger. And that's what we see here as we go down up and to the right. Size gets smaller, down and to the left, size gets larger. So when we think about all these trends sort of together, it explains what we kind of know happens when we look at the periodic table. When we take effective nuclear charge, it increases as you go this way and decreases as you go this way. When we take ionization energy, increases as you go this way, decreases as you go this way. When we take electron affinity, increases as you go this way, decreases as you go this way. When we take electronegativity, increases as you go this way, decreases as you go this way. And when we take size, it decreases as you go this way and increases as you go this way. So when we think about up here in the upper right of the periodic table, what we have are things that are very small in terms of overall size. There are things that like to hold on to their electrons. There are things that like to bring electrons towards themselves. And there are things that will want to take your electrons. And that's why when we think of nonmetals, we think of them as gaining electrons because of that. When we go lower left of the periodic table, we have things that are larger, which means the outer electrons aren't going to be held as tightly. You could remove the electrons relatively easy. They are not looking to gain electrons. They're not looking to take anybody's electrons. And that's why when we think about metals, they are typically the ones that lose electrons because of those periodic trends. Any questions on that there? All right, so let's take a look here. Which one should be the larger atom? If we look at sodium and chlorine, they're in the same period on the periodic table. Sodium is further to the left, which means it should be the larger atom, right? So size increases left and down. And obviously, chlorine is further to the right. Which should be the larger atom? That's lithium and cesium. They are in the same group, number one on the periodic table. Cesium is towards the bottom of the group. That's left bottom of the periodic table, which means it should be the larger atom of the two. Which is larger, the hydrogen 1s orbital or the lithium 1s orbital? So when we think about it here, it's going to be the hydrogen 1s orbital. And why would that be? Well, when we think about hydrogen, it has a +1 charge in the nucleus. When we think about lithium, it has a +3 charge, which means when we have our 1s orbital, which is in our first energy level, remember that because this is a greater positive charge, it is going to bring that 1s orbital closer to the nucleus than what we would see here with the +1 charge. And that's why we would expect the hydrogen actually to be larger. It's not going to draw that 1s orbital that close to the nucleus. Which one is lower in energy? In this case, lower in energy would be the lithium for the same reasoning. Because of that attraction, it's going to pull that 1s orbital closer to the nucleus, and by definition, that would mean that it is lower in energy than what we would see in the hydrogen 1s orbital. Yeah. Are you asking where the +1 and +3 come from? Yeah. That's basically remember, that's the nucleus in a sense. Yeah. So in the nucleus, there are protons and neutrons, right? And out of those two, only the protons have charge. So lithium, its atomic number is 3, so it has 3 protons. And that means overall the nucleus for lithium would have a +3 charge. And the atomic number for hydrogen is 1. So that means it has 1 proton in it, and overall it would have a +1 charge for the nucleus. And that's sort of what we're talking about, sort of the attraction between the nucleus and like the electrons and the orbitals. Yeah. Other questions? Bless you. Arrange these in order of increasing ionization energy. I think it actually is, so we'll just see how we got there. So we're looking at oxygen, fluorine, and sulfur. If we look on the periodic table, that is the arrangement right there. And basically, ionization energy increases up and to the right. So our highest ionization energy should be fluorine, and our lowest should be sulfur. And that obviously is what we see here. Our atomic size decreases as you go up and to the right. So fluorine should be the smallest. Sulfur would actually be the largest in this case. Questions on that there? Okay, we're going to now go to chapter 15. Only a couple more to go, I think, and we're out of chapters. So chapter 15 here is going to talk about solutions. So let's get into that. So many important chemical reactions and a lot of all biological reactions occur in an aqueous environment. So remember that an aqueous environment is those guys that have the AQ sort of symbol next to them. And what is an aqueous? It is actually a solution, and a solution is a homogeneous mixture of 2 or more substances. And remember that homogeneous means that everything looks the same throughout. And when we talk about a solution, there's really 2 parts to it. There is the solute, which is the smaller part of the solution, and then there is the solvent, which is the larger part of the solution. So for example, if we take sodium chloride, which is a solid, and we react it with or mix it with some water, our sodium chloride here would be our solute, and our solvent in this case would be the water. And they would come together as the sodium chloride would would dissolve in the water, and it would make a sodium chloride solution that would get the aqueous symbol next to it. Remember, there's a difference between aqueous and something that is a pure liquid, like water is a pure liquid. And a liquid is something that is basically just pure substance by itself. And here a solution is made up of those 2 things. Is water always your solvent? The answer is no. Water is not always the solvent, but it is a solvent for a lot of things because it works really well for a lot of things. How do you know what is the solute? It's pretty simple. The solute is always the name of the solution. So if you have a potassium chloride solution, the solute is potassium chloride. If you have a hydrochloric acid solution, hydrochloric acid there is the solute. So whatever the name of the solution is really the solute. If it is ionic, it's probably going to be water as your solvent. But again, water is not always the best solvent, as we'll talk about here in this chapter. But water does work really well as an effective solvent for a lot of ionic compounds and a lot of polar compounds. And again, it has something to do with what we talked about previously, which is water is a polar molecule. And because water is a polar molecule, it has a negative side to water, which is the oxygen side. It has a positive side to water, which is the hydrogen side. And again, that's a result of it having a dipole moment and unequal overall sharing of those electrons. And that works really, really well with, as we might have talked about previously, when you dissolve some type of ionic solid in it, it is able to basically interact with both ions. And for example, here with the sodium, the water can interact with the sodium ion through the oxygen ion as it is, or the oxygen atom as it is negatively charged, while the negative ion here can actually interact with the hydrogen side there of water, which is more positive charge. So that allows water to work really well as a very good solvent for things that are ionic. Water is also a really good solvent for anything that is polar as well. And again, that's because if it is something that is polar, it probably will use hydrogen bonding or dipole-dipole interaction. So again, that's very similar type of interactions, and that allows them to work really well. This process where we sort of dissolve an ionic compound in water is sometimes referred to as hydration. And as we probably have talked about previously, again, these water molecules basically keep these ions away from each other. And again, that is what allows it to dissolve. It is no longer visible to us because there's just so many water molecules that the salt gets kind of trapped in all those water molecules and we no longer can see it. Remember though, when you make a solution, because it is a homogeneous mixture, it is a physical change that's occurring. And as you've done before, if you were to heat this up, this solution, again, you could evaporate off all the water molecules, and then these ions would come back together and you would get your solid back. So a solution which is a homogeneous mixture is actually a physical change that's occurring when you make that, because again, you can very easily get back the original components by something like heating. And that's sort of what's happening here. Basically, the water molecules come, they pluck off the ions. This is like an ionic solid. Before it dissolves, it's basically all the ions hooked together through positive, negative attraction, and the water molecules come in. As you can see here, they come in, they pop off some ions.
An ionic solid dissolves in water because of its polar nature. Notice how water molecules become attached to the ions of a sodium chloride crystal in the process called hydration. Positively charged sodium ions attract the partial negative charge of the oxygen in water. A similar attraction occurs between negatively charged chloride ions and the hydrogen atoms, which have a partial positive charge. These interactions loosen the attractions between the ions in the crystal, dislodging them from the crystal. Additional water molecules surround the released ions, insulating them from attraction to other ions.
So again, the water molecules does allow it to dissolve. It actually sort of provides like a buffer that prevents those guys from coming back together, the two ions. As we've talked about in previous chapters, there's two types of bonding that we talked about. Ionic bond, which is between a metal and a nonmetal, caused by opposite attraction. Covalent bonding, where we do have sharing of electrons that occur. And remember that you can determine polarity of a bond based on the difference in electronegativity values. And that sometimes is important for solubility and how things can interact with each other. Again, you could have a molecule that is mostly nonpolar, but it could contain a polar bond. And by having that one polar bond, it's going to allow it to interact well with another molecule and mix really well because of the presence of that polar bond, which you again could figure out by the difference in electronegativity values. So when we talk about solubility in water, ionic compounds are definitely soluble in water. So if it's an ionic compound, it's going to dissolve in water with no problem. We do have non-ionic compounds that also dissolves in water. Sugar and ethanol are able to do that. Now, sugar and ethanol are covalently bonded things, but if we look at something like ethanol, which looks something like this, ethanol has kind of two parts to it. It has all these carbons and hydrogens. This is sort of a non-polar part. But as we were just talking about a second ago, it actually does contain this bond right here, which is actually a polar bond. Again, the difference in electronegativity between oxygen and hydrogen is going to cause the oxygen here to be more negative, the hydrogen to be more positive. And that works really well with water because in this situation, we have a hydrogen that's directly attached to an oxygen, which means that it can hydrogen bond. And the same thing as we see over here in water, it can hydrogen bond. And that's going to allow these guys to hydrogen bond with each other, water and ethanol. And that's going to make these guys pretty soluble in each other because of that. So because ethanol has this one bond that allows it to interact well with water, it's able to hydrogen bond with it and be soluble in water because of that. Now, solubility in something like this does decrease when this part gets really large or larger, and usually around 5 or more carbons, the solubility will start to drop to almost nothing. So if you have methanol, which has 1 carbon, ethanol, which has 2, propanol, which has 3, and so forth, they'll be fairly soluble. But as this part gets larger and larger, the nonpolar part, it kind of provides what's referred to as steric hindrance. It gets in the way of that molecule being able to interact well with water because it's just kind of big. Yes, sir. Exactly. So one of the things we're going to talk about is this idea of what's known as like dissolves like. So things will mix with each other, things will be soluble in each other if they're able to basically use those intermolecular forces we talked about in the previous chapter. If they're able to use a similar intermolecular force, for example, with that water uses, like hydrogen bonding is pretty much what water uses. So if they're able to hydrogen bond, it's going to be really soluble in water and they're going to mix really well. If they don't have anything that's similar, they're not going to really mix and stuff like that. Ionic compounds will always be soluble in water because they'll do what we talked about. I think we talked about it. It was called it like ion dipole interaction, right? And that's basically what happens when we dissolve a ionic solid in water and stuff like that. Yeah. Now, what about sugar? Sugar is a little bit larger of a molecule, but the one thing that sugar has sort of in its favor is it is actually littered with a bunch of OH groups. So it has a lot of OH groups all over it. So just like up here where if this part got really big, the carbon and hydrogen part, the nonpolar part got really large, the solubility would decrease. When you add more OH groups or something has more OH groups, it actually increases the solubility. So something like sugar has a lot of OH groups. So everywhere it has OH groups, it allows it a place to interact well with water and allows it to hydrogen bond, for example, with water really well. So here's methanol, also a organic molecule. That's a nonpolar part, but once again, methanol, much like ethanol, has that OH group, and that's going to allow it to do its hydrogen bonding with water and be very soluble in water. Here's our ethanol again doing its hydrogen bonding. Now, what about oil and water? Well, we know oil and water does not mix, and that is because pretty much what oil is nothing more than carbons and hydrogens attached to each other. So oil is essentially just a long chain of carbons. I won't draw them all, but a long chain of carbons and hydrogens attached to each other. And the carbon hydrogen bond is nonpolar. The carbon carbon bond is nonpolar. And this is a nonpolar molecule. Because of that, if you remember when we talked about intermolecular forces, nonpolar molecules is going to want to roll with dispersion forces. That is basically the only force that it can do. Those kind of weak temporary type forces. Water, on the other hand, as we've talked about, is going to want to try to roll with hydrogen bonding. So now these two things are definitely not going to have a way to interact well with each other and maintain that interaction over a long period of time. That again is, as we talked about, kind of how they will always kind of separate out from each other. They will be able to interact for a short period of time, but won't able to maintain that interaction. And that is because when you go to dissolve something in water or mix something in water, you essentially have to replace water and water interactions with something that's very similar. And when you take something like oil, it's really large and using dispersion forces, so it doesn't fit really well. So, for example, if you put a car in a garage, it probably will fit nice. But if you put like a semi truck in there, it's a little bit too big. You get some of it in, but it's not going to really fit really well in a garage. And that's sort of the idea with oil and water. It's just so nonpolar, so large. It has no way to replace those water-water interactions really well, and it will not do or mix really well. So that does bring up the idea, as I mentioned a second ago, of like dissolves like. And the idea of like dissolves like is essentially that anything that can use a similar type of intermolecular force that it uses with itself will be soluble in each other. So what that means is technically soluble is if you got ionic and polar things, they will be soluble in each other. If you got polar and polar things, they will be soluble in each other. And if you have nonpolar and nonpolar things, they will also be soluble in each other. You only really run into some problems and issues when you try to cross over polar and nonpolar. They typically will be insoluble in each other. And again, it's because they are trying to use way different types of intermolecular forces. When you take something that's polar and polar, they're going to use some type of dipole-dipole interaction, hydrogen bonding, dipole-dipole. They're going to be able to mix well with each other. If you take something that's nonpolar and nonpolar together, they're going to be able to use dispersion forces, both of them, so they're going to mix really well. If you take something that's ionic and polar, they're going to do ion-dipole interactions, so they're going to be able to interact well with each other. Again, you just get too much of a difference in the interaction between those two that they can't maintain it and they won't really mix together. Any questions on that there? So here is sugar. And as you can see here, even though it's a little bit larger of a molecule, it is littered with OH groups all over it. And everywhere there's an OH group gives it a place for it to hydrogen bond with water. And it's going to be very soluble in water. Down here, as I drew earlier, is essentially oil, and that is nonpolar all day. That is going to be using dispersion forces, and it's pretty long and big. It is not going to interact well with water for sure. By the way, that is also why, as I mentioned earlier, water is a really good solvent for things that are ionic and things that are polar, but water is a terrible solvent for something that is nonpolar because they're not going to mix. So you would want to use something, for example, that is nonpolar as your solvent if you're trying to dissolve something that is nonpolar. So although we kind of think a lot of times water is always like the best solvent to use, it is good for ionic and polar, but it is not good for nonpolar. You would actually need something more nonpolar for those things to dissolve in each other. That's what we typically see when we mix oil and water together. They do separate out. You typically the oil layers on top, the water layers on the bottom. And again, there's no way for those guys to interact well with each other. So when we talk about solubility, when one substance, like the solute, dissolves in another, it is said to be soluble. Salt is soluble in water. When one substance does not dissolve in another, it's said to be insoluble. Oil is insoluble in water. There is a limit to the solubility of one substance in the next, and it is based on temperature. And typically speaking, if you increase the temperature, you can get a lot more solid to dissolve in a liquid. If you decrease the temperature, you get less solid to dissolve in a liquid. Gases are always soluble in one another, and that's because gases are just by its nature flying around. So they're constantly mixing. So they're always going to be soluble in one another. Some liquids are also soluble in each other. So polar and polar, nonpolar and nonpolar liquids would be soluble in one another as well. Again, that idea of like dissolves like. The solubility of a solute does depend on temperature. When you have a higher temperature, you have a larger solubility of a solid in a liquid. At a lower temperature, you do have a larger solubility of a gas in a liquid. So, for example, if you had a liquid and a gas, at a lower temperature, your gas molecule is going to swim around or fly around a lot slower, which means it's going to stay in the liquid part for a lot longer of a time, and that will keep them mixed. Also, gases solubility depends on pressure. When you have a higher pressure, you have a larger solubility. And typically speaking, right, if you have a high pressure, you probably have a low volume, right? Boyle's law. And when you have a small volume, that means everybody's near each other and they're constantly mixing, right? Because there's much smaller volume. So you would have a much more mixing sort of occurring. Now, when we talk about solutions, there's a couple of ways we could describe a solution. As I mentioned before, there is a limit to how much that you could get to dissolve in a given amount of solvent. And if you have too much solute dissolved, you create what is known as a saturated solution. And a saturated solution is a solution where at that particular temperature, you pretty much hit the maximum amount of solute that you could dissolve. So if you hit what is sometimes referred to as the saturation point, you pretty much have hit the maximum amount of solid that you could get to dissolve at that temperature. And that means that if you try to dissolve more, no more will dissolve pretty much. It'll just start piling up at the bottom. What is the opposite case? The opposite case is you're not there yet. So you have what is known as an unsaturated solution. And in an unsaturated solution, you have not hit that point of no more will dissolve. So you could continue to dissolve. So if you put more solid in an unsaturated solution, it will continue to dissolve. It will continue to dissolve until you get to a saturated solution. And at that point, no more will dissolve. So unsaturated, you can still have more solute to dissolve. Saturated, you pretty much have hit the point of maximum amount of solid that will dissolve at that point.
The flask contained it.
Let's talk about that one too. So before I watch that video, another way that you could classify a solution is one that's known as a supersaturated solution. And a supersaturated solution is a solution where you have too much solute dissolved in the solvent. So a supersaturated solution is one where you have too much solute dissolved in the solvent. It is kind of an unstable solution. How can you make a supersaturated solution? Well, pretty simple. You actually, for example, if you took something like a test tube or a beaker, whatever it may be, and you heated it up. And if you heated it up and you took some solid to dissolve in it, by heating it up, you're raising the temperature. So, as we just talked about, what that's going to allow you to do is get a lot of solid dissolved in here. So, you're going to get a lot of solid to be able to be dissolved in this test tube because you're heating it up, you're increasing the solubility of that solid with the solvent. What happens then is you typically would take the test tube or the beaker and then you would let it cool back down. Now, what's happening when it cools back down is as it cools back down, the solubility is going to change because now the temperature is a lot less than it was when you heated it. The problem is you've already got everything dissolved in it. So this solution at this point, once it cools down, is now a solution that has way too much solute dissolved in that solvent. It is so unstable that if you just took like a speck like that of whatever you dissolved in it and you drop that one little speck in, it would be enough to kind of push it over its limit and go way too much at this cooler temperature. And what you would see is it would go from the liquid state and you would actually see all of the solid start to come out of the solution by just adding that one little crystal. And it would go from a solution to now like a rock hard solid at this point. All of the solid will come out of solution because you kind of went way over the limit at this point. By adding that one little sort of speck of it, it will allow it to do that. These solutions are so unstable that it could sometimes happen by just simply knocking the beaker a little bit. Like you shake it too much, you move it too much. That's actually enough sometimes for it to just cause everything to come out of solution without you actually adding the solid to it. I've done that in many demonstrations. I moved it too quick and all of a sudden it just starts coming out of solutions and stuff like that. And that's what we're going to see here in this video. And I think we'll see it tomorrow, I think.
The flask contains a supersaturated solution of sodium acetate in water. A small crystal of sodium acetate will be added to the solution.
So what they have in the flask is a already supersaturated solution that they made, like I described. They heated it up. They got a bunch of solid to dissolve in there at the higher temperature, and then they just let it cool back down without touching it. And now they're going to take one little speck of what they dissolved in there and drop it in.
Focus your attention on the portion of the solution to which the crystal is added.
And that's all the solid now coming out of the solution because it's way too much in there dissolved to begin with.
Here is the process again in slow motion.
Super slow replay. I like it. And that thing at the end there is going to be like rock hard. There's no liquid left at that point. Pretty much all the solid just jumped out of the solution. That's what I was saying. I've knocked that flask before, and it's just enough to sometimes just cause that to happen. Let's talk about some other ways to describe solutions. A concentrated solution is a solution that contains a relatively large amount of solute molecules. By the way, when we have a solution, it is the solute molecules that are the things that are actually reacting. A dilute solution is a solution that contains a relatively small amount of solute, a little bit more solvent. Classic example, right? You get the giant soda right before you come to class with all the ice. You leave in your car, you come back out after class, all your ice is melted, right? Your soda now feels a little bit more dilute, right? It is watered down from all this ice that melted, all the water that came as the ice melted. Most of the time in chemistry, we buy things in concentrated solutions, and most of the time what you work with in lab is dilute solutions. They dilute it down. Those are all those numbers that you see on the bottles where it says like 6M or 2M molarity, which is a concentration. Those are, the concentration of what's in those bottles. So let's talk about actual concentrations and ways to calculate it. The first type of concentration we're going to talk about is what's referred to as mass percent, or sometimes abbreviated percent mass to mass. And the mass percent is the mass of the solute divided by the mass of the solution times 100%. Now, it is actually the bottom part here that's really important and where most people screw up on. Remember that the solution, as we talked about, are two things. It is the solute plus the solvent. So you do want to make sure on the bottom there that you get both of those things together when you actually calculate it. Most of the time, or a lot of times, people will just take the solvent and not the solute. Why is that an issue? It's an issue because in these type of problems, they typically will give you that information separate from each other. So they will give you the solute, they'll give you the mass of the solvent, and it will be separate from one another. So you do want to make sure you get it. So for example, if I had a 4.5% by mass potassium chloride solution, you could actually turn that, for example, into a conversion factor, and that would mean that I would have 4.50 grams of KCl in 100 grams of solution. Or you could flip it around and go 100 grams of solution, I would have 4.50 grams of KCl. So sometimes when you're doing these type of problems, you definitely could plug and chug into the equation, but sometimes taking a dimensional analysis approach, if you're given the percent mass to mass, you can use it as a conversion factor and kind of use it in a dimensional analysis sort of calculation. Question on that there. Now, in addition to mass percent, there's a couple of other percent concentrations. The next one is percent volume to volume. That is the volume of solute divided by the volume of solution times 100%. This is kind of like milliliters divided by milliliters, as the other one's grams over grams. We also have percent mass to volume. That is the mass of the solute divided by the volume of the solution times 100%. That's kind of like density, grams on top, milliliters on the bottom, basically, as a percentage. So these are three sort of percent concentrations. They work the same. So if you had a 4.50% volume to volume potassium chloride solution, that would mean you have 4.50 milliliters of potassium chloride and 100 milliliters of solution. Or in 100 milliliters of solution, you have 4.50 milliliters of KCl. And same thing here, if you had 4.5% mass to volume KCl, you would have 4.50 grams of KCl and 100 milliliters of solution. Or in 100 milliliters of solution, you would have 4.50 grams of KCl. Unlike the mass to mass percent, a lot of times you don't have to be too concerned about that. Usually they'll oftentimes give you the volume of the solution, but definitely for mass percent, they do like to break up the solution into the solute and the solvent when you're doing it. Now, again, for any of these, you can just plug and chug into the formulas, or again, you could kind of use them as a conversion factor if you're given the percentages and take a more dimensional analysis approach. Any questions on those there? Mass to mass, which is our mass of our solute, divided by the mass of the solution times 100%. Here, the calcium chloride here is our solute, as it is the smaller part. Our water here is our solvent. So we got our solute here of 2.5 grams. We have our solvent of 50 grams. Remember, if we add these together, that gives us our solution, which is 52.5 grams. Again, not 50, which is just the solvent. Putting that in, 2.5 grams divided by 52.5 grams times 100%. Looks like 4.76%. And you could leave this as mass to mass, and you could put calcium chloride if you like in that particular case. Question on that calculation there. So again, super common. People just roll with the solvent only. Yeah, so make sure you get that one. All right, let's then take a look at another one. If there's no questions, concentrated hydrochloric acid contains 37.2% by mass HCl. What is the mass of HCl that's contained in 35.5 grams of a concentrated hydrochloric acid solution? Okay, so let's take a look. We are given in this case the percent mass to mass, which is 37.2%. We're looking for the mass of the HCl, which is our solute, and I know that because the name of the solution is always the solute. So obviously, if I'm looking for the HCl, that is our solute. It's contained in 35.5, so I know that that is the mass of the solution is 35.5 grams. Now, you definitely could, if you wanted to, just plug and chug into our equation here. I personally am going to take a more dimensional analysis approach. Again, as we've talked about many times, it may help you not have to rearrange this equation or maybe mess it up. So when I see 37.2%, that means I have basically 37.2 grams of HCl in 100 grams of solution. Or I can flip it around, 100 grams of solution. There is 37.2 grams of HCl. So I definitely have my mass of my solution, so 35.5 grams of my solution. Again, all I have to remember is opposites cancel, so that's going to do it for me there. And we're going to go 37.2 grams divided by 100 grams of solution. And if we do that there, 35.5 times 37.2 divided by 100, 13.2 grams of HCl. Now, this is essentially the exact same math, obviously, that you're doing. If you rearrange our formula up here and solve for the mass of the solute, it would be the percent mass to mass times the mass of the solution divided by 100%. And that's essentially what we did down here. Any questions on that one there? All right, then let's talk about probably the most common unit of concentration, and that is molarity. And molarity is pretty much the one that you use the most. Molarity is abbreviated with a big M, and it does stand for moles of solute over liters of solution. And you could think of molarity as a formula, moles per liter. We can solve for really any one of these three things. If we want liters, that is moles divided by molarity. If I want moles, which is a common move, that is liters times molarity. So those are three ways that we rearrange this equation and use it to solve. And that is a very, very common way that we use it as well. The higher the M value you see, the more concentrated it is. So if you see something with like an 18 molar, that's pretty strong acid. If you see something with like 0.1 molar, it's not very strong at all in comparison. Now, I will say if you're going to do this one here, you should always convert the volume into liters. That way it will cancel out correctly and you'll have the units that you need. Um, if you multiply it by milliliters, for example, here, if you take milliliters times molarity, it doesn't actually give you moles, it gives you millimoles. So you'll be off by a factor of 1,000 probably in your calculations. So if you're ever using molarity by itself, it does need you need to convert the volume into liters because that will give you moles, which is essentially probably what you're looking for. Now, when we talk about a solution being 1 molar, it contains basically 1 mole of solute per liter solution. And if we have a 1 molar solution of sodium chloride, that means that we have 1 mole of sodium chloride dissolved in enough water to make 1 liter of solution. And it will contain 1 mole of sodium ions and 1 mole chloride ions. Now, how does concentration work when you break something apart? So, for example, when we take something like sodium chloride and it's going to, in solution, break apart into sodium ions and chloride ions, sometimes you're not interested maybe in the whole thing, but you are interested in like the individual ions. And how molarity works is this. It works just like stoichiometry. So this is a 1-to-1 relationship between the whole thing and the sodium ion, which means you take 1 times the molarity, and that would give you 1 molar sodium ions. This is a 1-to-1 relationship, and that would get you 1 times the molarity, which would be 1 molar chloride ions. They're not additive, but that is how it works. What is actually the calculation that you're doing? You're really just doing a stoichiometry sort of calculation on mole to mole relationship. So when you take 1 molar sodium chloride, that big M stands for moles per liter. And if you do just some stoichiometry, it's a 1 mole to 1 mole relationship. 1 mole of sodium ions, 1 mole of the whole thing. Moles of the whole thing cancel. And that leaves you 1 mole per liter of sodium ions, which is the 1 molar sodium ion concentration. So that is how you get there. The quickest way to do it, though, is just to multiply the concentration by the coefficient in terms of the ion. Now, let's talk a little bit about this big M. Say we have sodium chloride here. So if you were to do a calculation involving molarity and you're given the molarity, I highly, highly recommend that you get rid of the big M and you turn it into the 2 units that are there, which is 4.5 moles per 1 liter of sodium chloride. The number always stays with the moles part and it's always per 1 liter. Or you can flip it around and use it as a conversion factor. A liter is 4.50 moles of sodium chloride. Why should you do that? You should do that in calculations so you could do a dimensional analysis. But more importantly, in my experience, when people leave the big M in calculations, they have absolutely, positively no idea about the volume part of it. They're not sure where it's at. Is it on the bottom? Is it on top? Should they multiply? Should they divide? So here, if you write out both units, you'll be able to see them and hopefully it'll remind you to make sure you use it correctly. So that's a super common error people make. They leave the big M and they just have no clue about the volume part of the calculation, where it is, what they should do with it, or even if it's there, they just think moles when they see the big M and stuff like that. So um, I would always get rid of the big M in calculation, take a more dimensional analysis approach, and that's really a good way to sort of do that. So let's talk a little about the concentration of ions. As I mentioned before, uh, if you had something like sodium chloride, as we saw, but let's say we had something like calcium chloride solution. When calcium chloride breaks apart, it breaks apart into a calcium ion and two chloride ions here. Now, again, if this guy was 2 molar, was this concentration, this would be a 1-to-1 relationship between the whole thing and the calcium ions, which means it is 1 times 2 molar, and it would be 2 molar calcium ions in this case. But when we get to the chloride, it is a 1-to-2 relationship, and that means that we have to multiply the concentration by 2 in this case. And the concentration of chloride ions floating around in there would be 4 molar in this case. So again, it's not additive, like 4 and 2 doesn't equal 2, but it's proportional wise. You basically get a 2-for-1 deal when you do that, right? So if you took calcium chloride and you dropped it in here, you're going to get a calcium and 2 chlorides. So you get 2 of these per one of those. So it is twice as concentrated in chloride as it is in calcium, basically. Question on that there. So if I had Na2SO4, this would break apart into 2 sodiums and a sulfate. And if the concentration of this guy was 0.1 molar, again, it's a 1-to-2 relationship here. So we would take 2 times 0.1 molar, and it would be 0.2 molar for sodium ions. And it is a 1-to-1 relationship between that and sulfate, and it would be 1 times 0.1 molar, which would give us 0.1 molar sulfate in this case. In this case, it is twice as concentrated in terms of sodium as it is sulfate. Yes, sir.
One, that's 1-to-2 ratio, and there's 2 Na up. Like Na2 means there's 2 sodiums, and Na means there's 2 sodiums.
It does. So this means there are 2 sodiums, which is what that 2 means there. No, there's only one of the whole thing, right? So this is one of the whole thing here. So there's one of the whole thing, and you get 2 of these guys. So if you took if you took a beaker like this, right, and you took one of these whole units, right, and you tossed it in to dissolve it in water, basically, what's going to happen when that thing goes for a swim is you will get 2 sodium ions formed, and 1 sulfate ion will start floating around. And that's basically what these numbers show you. You got twice as much sodium ions floating around as you do sulfate, right? So it's twice as concentrated in sodium as it is in sulfate. Yeah. Other questions? So again, sometimes in problems, you're not maybe interested in the whole thing, but you may be interested in just an ion or so. And this is a quick way as to how you can relate the concentration of the whole ionic compound into the concentration of the ion. All right, so why don't you try one here? Calculate the molarity of a solution prepared by dissolving 15.6 grams of potassium bromide in enough water to make 1.25 liters. Potassium 3910 and bromine 7990. We do have the liters given to us, so we're good to go on that. I will say very commonly in these type of calculations, the 1,000 milliliters to 1 liter conversions lose a lot. So a lot of times you are given things in milliliters and you need to convert it to liters. So that conversion is used a lot. Here we do not have the moles, but we do have the grams. So that's not a problem because we know we could go to the periodic table here and basically get the molar mass. And if we do that, we're just going to add these together. That's 119 grams per mole. We'll use that as our conversion factor here. Grams are going to go on the bottom so that they cancel. Moles of KBr will go up on top, so we end up with that. And that's going to get us here, looks like 0.131 moles of KBr. That is the top number that we need. So now we have everything that we need. So the molarity here will be our moles divided by our liters, which is already in liters. And we will end up with here 0.105. Now the units here do not cancel, so you can leave it in one of two ways. The number always goes with the moles, and it's always per 1 liter, so you can leave it like that. Or at this point, you could turn it back into the big M KBR as well. So you could do that either way in this case. Off any question on that calculation there? Yeah. Yeah, so on this one, on this one, it is solute and solution. I would say in most cases, they will either, they may say you used enough water to get this much volume of solution. So more commonly in these type of ones. So unlike the percent mass to mass where they kind of break up like the solute and the solvent, here they oftentimes will talk about more the solution. And they may mention water, but it'll probably be in the context of you added enough water to get to this volume. I would say more cases with these, you'll probably be given a volume in milliliters. It just converts to liters as more. So what you have to do. Other questions? Yeah. All right, let's try another one here. What is the mass in grams of sodium nitrate that's required to make 2.5 liters of a 0.15 molar solution? By the way, before we do that, I'll just come back here. So basically what this is telling us is if we wanted to make this solution with this molarity of 0.105, we would weigh out 15.6 grams of KBr. We would actually use water as our solvent because it's ionic, and we would add enough water to dissolve it to 1.25 liters. And if we mix it all together, then we would have a solution at that point of 0.105 molar would be the concentration of solution. So this is actually how you would go make that solution if you needed to. All right, so let's go to this one and give this one a go here. So we're looking for the mass in grams of sodium nitrate to make this solution that has this molarity. Sodium is 2299. Nitrogen is 1401. And oxygen is 16. We're looking for grams. We are given the molarity. So that should help you think about the molarity sort of formula. I do have the molarity given to me at 0.15 molar. So I have that. I do have the volume there in liters of 2.50 liters. So if you weren't sure where to go to begin with, it does sort of maybe make sense that the only thing you're missing is moles here. And you could get moles from that information. And that would be helpful because we know how to go from moles to grams, which is ultimately sort of what we're looking to do. Now, you definitely could just plug it into this equation, but once again, as I mentioned, it is oftentimes better to maybe take a dimensional analysis approach. So when I am given the 0.150 molar solution, that means I have 0.150 moles per liter of sodium nitrate. Or again, I can flip it around and put the liters on top and do 0.15 moles of sodium nitrate on the bottom. So I can take my volume here, and again, I don't have to worry about rearranging this equation. All I have to remember is opposites cancel, so I got liters up on top. That means I need liters here on the bottom, and that would be the right way to use it here. Again, we're multiplying the top, dividing the bottom. Liters cancel, and that gives me 2.5 times 0.15, 0.375 moles of sodium nitrate. At this point, it's now just a conversion between moles to grams, and that is the molar mass from the periodic table. It's going to help me do that. So I got 2299 for my sodium. I got 1401 for my nitrogen, and I got 3 times 16 for my oxygen in this case. And that's going to get me here. Looks like 85 grams per mole. And again, going to use that as a conversion factor. I want grams up on top and moles on the bottom here. So again, when we multiply and divide, those are going to cancel and leave us with grams. And that's going to get me here, call it 31.9 grams of sodium nitrate here in this case. Questions on that? Yeah. Because things in opposite locations when you do dimensional analysis cancel. So liters are up on top and liters are on the bottom. The, here, or those are just your two possible conversion factors that you could get from this number here. So again, it's a really good idea to get rid of the big M, so you can actually see both units. Because as I mentioned earlier, a lot of times when people just use the big M in the calculation, they literally have no idea about the liters part of it. So they're not sure, for example, when they would get down to this part, for example, they're not sure if they should multiply or divide or really where the liters are. So from this big M, stands for moles per liter, you could turn that number into this as a conversion factor or that as a conversion factor. So you're not going to use them both, but you could just use one of them. All right, so why don't you give this one a try? Actually, I think I might have done this one earlier. Well, we not. Well, I did a different one. So for each of these individual solutions, what are the concentrations of each of the ions that are present? So for this one here, we want to know what is the concentration of the sodium, what is the concentration of the sulfate, and for this one, what is the concentration of the potassium, and what is the concentration of the chromate. So take a moment. What would be the concentration of each of these ions in those two different solutions? Okay, so let's take a look at this like we were talking about earlier. Again, if we have this solution, we do want to think about how it's going to break apart into its ions. When it's in a solution, since it is a strong electrolyte, it will not stay together, so it will break apart into these two guys here. And again, as we talked about earlier, the way concentration works, this is a 1-to-2 relationship. So for the sodium ions, we would have to multiply the molarity by 2, gives us 2.4 molar in terms of our sodium concentration. It is, as we can see here, a 1-to-1 relationship. So basically 1 times it gives us 1.2 molar for sulfate. Once again, we do get like a 2-for-1 deal here. So we have twice as much sodium ions floating around. So again, it's going to be twice as concentrated in terms of the sodium ions. Any questions on that one there? Taking a look at the second one, K2CrO4. Again, this is going to break apart into 2 potassiums and a chromate here. And if this is 0.75 molar, it is a 1-to-2 for this one. So we would take 2 times that to get our concentration of 1.5. molar potassium ions. It is a 1-to-1 relationship, so it would be the same concentration here for our chromate as it is for the whole thing in this case. Any questions on that there? All right, so let's take a look at one more here that involves this type of thing. How many moles of calcium and chloride would be present in 42 milliliters of a 0.35 molar calcium chloride solution? So give it a go there, see what you come up with. Okay, let's take a look. So in this particular case, we're looking for the moles of the ions in the solution. Here we do have the volume, 42 milliliters. We have the molarity given to us, 0.35 molar calcium chloride. So again, if we think about our molarity, moles per liter, we do have the liters, is in milliliters, but we could get to liters. We do have the molarities, so we could use this just to get to moles. Again, that is my approach I think I'm going to take. I do need to convert this into liters whenever I'm using molarity and volume. Volume needs to be in liters, so 42 milliliters. There is 1,000 milliliters in a liter, 0.0420 liters. Once again, I'm going to do more of a dimensional analysis here with the conversion factor rather than just plug it into the equation. So that means I have 0.350 moles of calcium chloride per liter. Are again my other option in terms of a conversion factor. Liters can be up on top, 0.350 moles of calcium chloride on the bottom. Since I have the liters here, I'm going to use my conversion factor. Opposites cancel. So I'm going to go with this. And that's going to give me 0.350 moles of calcium chloride per liter. Liters are going to cancel as I'm multiplying, then dividing. And that's going to give me here 0.04, whoops, come here, 0.0420 times 0.350, 0.0147 moles of calcium chloride. Now, again, I'm not interested in the whole thing here. I am interested in the ions. So I could use my knowledge of how this guy is going to break apart in solution into a calcium and 2 chloride ions. And really at this point, I could do 2 calculations. I could use that sort of mole to mole relationship. It's a 1-to-1 relationship there. So for every 1 mole of calcium chloride, I get 1 mole of calcium. And that gives me 0.0147 moles of calcium ions. I then could use my moles of the whole thing and do my mole to mole relationship between the whole thing and chloride, which is a 1-to-2 relationship. So for every 2 moles of chloride, it is 1 mole of the whole thing. And that's going to give me here, times that by 2, 0.0294 moles of chloride. Question on that. Now, you could have, if you wanted to, right off the bat, just did this like we did previously, 0.35 molar. It's a 1-to-1 relationship, which means this guy's concentration would be 0.35 molar. It's a 1-to-2 relationship, 0.7 molar there. And you could have just done 2 separate calculations with the concentration of the ions. It should come out the same if you want to do that approach as well. So either way would work there. Any questions on molarity, how to calculate molarity, any of those things? So.